What I'm going to talk during the next hour is what is Bayesian framework and what is its key differences from the classical approach, for the classical framework to probability theory known also as a frequentist approach. Then we'll discuss how we can build Bayesian machine learning models and what are their specifics. What is full Bayesian inference, and we end up the first lecture with a consideration of conjugate distributions. So this is the very important particular case when full Bayesian inference can be done extremely efficiently in the closed form. Okay, so first let us review, and again, I stress that this is introductory lectures, and I hope that all of you are more or less familiar with what I'm going to tell today. So this is normal, and if you feel a bit boring, so you may just have a walk, since the weather is beautiful today. Okay, so the key notion with which we are going to work is the conditional distributions. Conditional distributions play a very important role in probability theory, especially when we talk about the revealing of hidden dependencies within the data, and this is exactly the topic of modern machine learning. So what is conditional distribution? By definition, this is simply a relation of joint distribution over marginal. Or in the mathematical form, the conditional distribution of x given y is simply the relation of joint distribution P of xy over marginal distribution P of y. And the interpretation is pretty simple. The conditional distribution shows how the distribution over x has changed after we have observed y variable, after we have observed the particular value of y. Why should change? Well, we assume that x and y are somehow related to each other. And if they're not, if x and y are independent variables, then of course the joint distribution decomposes as a product of P of x times P of y. P of y vanishes, and we obtain that P of x given y simply equals P of x. So this is nice, but this is not interesting. The most interesting is the situation when x and y are interdependent. And then observing some variables, we can update our uncertainty or our knowledge about the distribution of another variable. And the direct consequences of the definition of conditional density are those two rules, product rule and sum rule. So according to product rule, any joint distribution can always be decomposed as a product of one-dimensional conditional distributions. And the condition becomes less and less. So, for example, P of x, y, z can be decomposed as P of x given y, z times P of y given z times P of z. P of z is already unconditional distribution. And of course, we can rearrange the order of the variables and then write down another decomposition. This is what we can always do. And this is one of the ways of how we usually define joint distributions of a huge set of variables. So we usually define them in some kind of chain rule by establishing the corresponding conditional distributions, which are generally much easier and much more interpretable than the establishment of the joint distribution itself. And another rule is sum rule, which states how we can obtain marginal distribution if we have access to the joint distribution. So any marginal distribution can be obtained simply by integrating out or by marginalizing the unnecessary variables. So if we have a joint distribution over x and y, and we would like to get unconditional or marginal distribution over y, we simply take the joint and integrate out x. So that's pretty simple. And based on these two rules, we can always construct and compute arbitrary conditional distributions from the joint. So this is very nice, and this is why people work with probabilistic models, and by probabilistic model I mean the definition, the establishment of a joint distribution over all set of variables which are involved in our problem. So if we have access to the joint distribution, we can always compute any kinds of conditional distributions. For example, assume that we have a joint distribution over three groups of variables, P of x, y, z. Assume that we observe x, and we would like to predict or to estimate the y variable. And we do not care about z. So this means that we'd like to be able to compute this conditional distribution, which would be our prediction. P of y given x. And we have access only to this joint distribution P of x, y, z. So any ideas of how can we compute this conditional distribution? Exactly, right. So that's it. By definition, P of y given x is simply a ratio of P of xy over P of x. And to get those two marginal distributions, we simply take the joint and marginalize them with respect to unnecessary variables. Yeah. So this result, this is how we should do in theory. In practice, of course, the question is whether we can take these integrals in a closed form or not. But in theory, this is what we should do. And that's why I'm saying that if we have a joint distribution, we have the full probabilistic model, and this means that at least in theory, we're able to build any kinds of predictions. So if we observe some group of variables, we can say something about remaining variables or about some subgroup of remaining variables. Okay, and another direct consequence of those two rules is famous Bayes theorem, which was proved in the 18th century, so a long time ago. The idea is pretty simple. If I have access to the conditional distribution over x, y, and we have access to our prior P of y, we can always transform our prior distribution to posterior distribution, P of y given x, well, just by using the definition of conditional distribution and by applying the sum rule. So in conceptual form, this theorem can be written as follows. So our posterior distribution equals the product of our likelihood times prior divided by normalization constant known as evidence. And the theorem is quite important, and conceptually, what it allows us to make. It allows us to update our uncertainty or our knowledge about the variable to be estimated. In this case, this is y, by observing some variables, some data, which are somehow related to y. And by this data, I mean, in this case, I mean x. And the update is actually pretty simple. So we simply take our prior distribution, which encodes our uncertainty about possible values of y, and we multiply it by likelihood function. And the likelihood function shows how probable is to observe what we observe, to observe x, if y had a specific value. So we simply take the product, and in order to ensure that this is a correct probability density function, we need to renormalize it by normalization constant. Then in the right-hand part expression, we have a correct probability density with respect to y. And this is exactly what we wanted. So this is Bayes theorem. Okay, now let's consider the classical statistical inference problem. We are given a set of samples from some distribution which is known up to parameters theta. And the task is to estimate the parameters theta based on the observed data. So there are two main approaches to how to do that, the two main approaches to statistical inference. The first one is classical, known also as Frequentist approach, while the remaining one is Bayesian framework. So according to Frequentist approach, we simply use maximum likelihood estimation, with which all of you, I guess, are familiar. So we take the likelihood function, we substitute the observed data there, x large, and given the assumption that the data is IID, independent, identically distributed, this is simply product of individual likelihood functions, P of xi given theta. So we compute this product and we try to find, and we consider it as a function of theta, and we try to find the maximum value of theta. Or equivalently, we can take the log, and then our product becomes summation. In practice, this is much easier to optimize when we switch to the summation. Okay, so we still have a function of theta. We find its argmax, and this is a maximum likelihood estimate, which is known to be optimal under some very general conditions, which we all studied in university in our theory of probability courses. Alternatively, from Bayesian point of view, what should we do? Again, we have some data, x large, which consists of n objects, and we would like to estimate theta, to extract as much information about theta as possible, which is contained in our data. So from Bayesian point of view, we should simply apply Bayes theorem. So first we should start with the prior distribution. So we should somehow encode our preferences, our uncertainty about the possible values of theta in terms of probabilistic distribution. And surprisingly, it appears that in practice, in many cases, this can be done in a very natural way. So it's not a restriction. And then we apply Bayes theorem and end up with a posterior distribution. So what's important here? Unlike the Frequentist framework, instead of obtaining just point estimate on theta, the result of our inference is a distribution. So we start with a distribution and we end up with a distribution. And it appears that this is very nice, because now if imagine that some new data arrived. So we can update our distribution, our posterior over theta, by using P of theta given x as a new prior. Because this is still a distribution. So we started with distribution, we ended with a distribution. So we can now use this posterior distribution as a new prior distribution and update it when new data arrives. And in this case, we no longer need the knowledge about the data itself. All information which was all information about theta which was contained in our observed data is already in our posterior distribution. So when we computed this posterior distribution, we no longer need the old data x large. So this is a quite interesting property. And now let's consider a simple example. Let's assume that we have a coin with unknown probability of head. And this is our theta parameter, and we would like to estimate the probability of head. We toss a coin twice, and in both cases we observe heads. So now the question is, what can we say about the probable values of theta? Well, from Frequentist point of view, and this is actually why this framework is called Frequentist, we apply a maximum likelihood estimation, and the maximum likelihood estimate is simply frequency of heads. So this is the number of heads over the number of tosses. And since here there were just 2 tosses and 2 heads, so maximum likelihood estimation is that theta ml equals to 1. ml, maximum likelihood, not machine learning here. So I think that most of you would agree that this is a bit counterintuitive. And common sense hints us that probably we should not be so sure that the coin has really 2 heads on both sides, on both sizes. Probably the amount of data is too limited to make so radical conclusions. And this is where Bayesian framework comes in. So we start from prior distribution, and the prior distribution reflects our prior knowledge about possible values of theta. And we know that the most of coins with which we deal in our real life are unbiased, are fair coins. So we may encode our uncertainty about the possible values of probability of a head in terms of prior distribution, and it will have probably a mode around 1/2, because the most of coins are fair. And after we apply Bayes' theorem, we end up with a posterior distribution, which is still pretty close to prior distribution, but a bit shifted towards 1, because the data encourages that the probability of heads is probably larger than the probability of tails. But still, this is a distribution with a very large variance, so we're still very uncertain about the particular value of probability of head. Now consider that, assume that we continue our experiment, and we toss a coin 1,000 of times. And we observe about 500 of tails and about 500 of heads. Probably currently the amount of data is quite enough in order to make point estimate, and in order to say that the coin is fair or almost fair. So given this amount of data, we can reliably apply maximum likelihood estimation. And this is probably the main difference between Frequentist and Bayesian frameworks. So the main, I would say, philosophical difference between these 2 approaches is the interpretation of randomness, of what we can call random variable. So from Frequentist point of view, random variable is the result of some process which cannot be predicted by any means. It's unpredictable by definition. All we can do is simply to collect some statistics and to use some statistical inference tools. From Bayesian point of view, random variable is the outcome of completely deterministic process, but some of the factors which influence the outcome are unknown for the observer. And different observers may have different knowledge about those factors, so they may have different uncertainty about the outcome of the process. But the process itself is completely deterministic. So this is the philosophical difference, but it's still quite important because all other mathematical differences are derived from this philosophical concept. And if we think a bit, we'll surprisingly discover that the most of random variables with which we deal in our real life are random from Bayesian point of view, not from classical point of view. Really, if we consider, for example, the example above, the tossing coin, actually we know that the coin obeys the laws of classical mechanics. So if we knew the initial conditions, if we knew the strength, the momentum with which we toss a coin, we would definitely predict the outcome, whether it will be head or tail. And the only reason why we can't predict it in an exact manner is because we do not know these initial conditions with which we toss a coin, and the characteristics of environment, the characteristics of a surface, where it lands, and so on. But if we knew all that, the outcome would be completely deterministic. And there are many more examples, so you may imagine it by yourself, and it appears that almost everything with which we deal in our real life and what we traditionally call random is random from Bayesian point of view, not from the classical point of view. And the question to you, whether any of you can imagine some random variable which is random from a classical point of view, which cannot be expressed as a deterministic process with unknown factors. Radioactive decay, right. I don't know whether you deal with radioactive decay in your real life. Me, fortunately, no. But yeah, this is one of the examples, and probably all other examples which I know are all related to quantum mechanics, where we have this famous indefiniteness relation by Heisenberg. And radioactive decay is a particular case of those quantum effects. So in quantum mechanics, there's really randomness which cannot be predicted by somehow, at least according to our current level of knowledge of modern physics. Everything else is random from Bayesian point of view. So actually, it's not random, it's deterministic. And from this point of view, it appears that the distinction between random and deterministic variables disappears. So in classical framework, we strictly divide all variables into random and deterministic. So deterministic variables can be unknown for us, but they're still deterministic, they're not random variables. From Bayesian point of view, everything can be treated as a random variable. Even if we know the particular value of some variable, we can say, well, it's random, but it has a degenerate distribution. So this is just delta function, and all probabilistic mass is centered at one point. But we can still use the mathematical tools from probability theory. So that's nice, and immediately from that, there are some consequences. One of them is the statistical inference tool. So maximum likelihood estimation is replaced with the Bayes theorem. The point estimates are replaced with the distributions. So instead of using just point estimates, we are using distributions. And finally, my favorite line is the applicability. So we know that maximum likelihood estimation is optimal statistical inference tool. Yep, it's really so, but under some conditions. And one of the conditions is that n should be much larger than d. N is the amount of data which we use during our statistical inference, and d is the dimensionality of parameter to be estimated. In our case, this was theta. So the dimension of theta should be much less than the amount of data we use for maximum likelihood estimation. Only in this, under these conditions, maximum likelihood estimator is known to be optimal. Of course, we can use maximum likelihood estimation even if this condition doesn't hold. But in this case, it becomes just a reasonable heuristic, and we lose all theoretical guarantees of its optimality. To the contrary, Bayesian estimation, Bayesian framework is applicable for any number of n. Even if n is equal to 0, we can still use Bayes theorem, but of course we'll end up with a posterior which equals to prior, because I have no data. If n equals to 1, 2, 3, we can already update our uncertainty. We can already extract some information in a mathematically correct form. And now the question can be whether these two approaches contradict to each other. And the brilliant answer is no. There's no contradiction between classical approach or frequentist approach and Bayesian framework. And it can be pretty easily shown that under some general regularity constraints, if we perform Bayesian estimation under the conditions when n is much larger than d, our posterior distribution converges to delta function centered at maximum likelihood point. This is exactly maximum likelihood estimation. So this means that you can treat either the classical approach as a limit case of Bayesian framework, or alternatively you may treat Bayesian framework as some generalization of classical statistics for arbitrary amount of data. But there's no contradiction. So from this point of view, you may always be Bayesian, and when maximum likelihood becomes optimal, you'll simply converge to maximum likelihood estimate. Okay, so what are, to summarize, what are the advantages of Bayesian framework? First of all, we can encode our prior knowledge, our prior information about possible values, about preferences of variables to be estimated in terms of prior distribution, and then we can simply update it using Bayes' theorem. Prior distribution can also serve as some kind of regularization. Remember that case with the tossing a coin twice. If we would not be Bayesian, we simply end up with a probability of head equal to 1, and this would be a classical example of overfitting, with which we are all familiar since we are all doing machine learning. So if we have prior distribution, we regularize, we do not allow the model to overfit the data. This is especially crucial when the amount of data is limited. And although you may tell that in modern deep learning we have to deal with a huge training data sets, we should always remember that, yeah, we are dealing with large data sets, but the amount of parameters to be estimated, the amount of weights on our deep neural networks is much larger than the amount of training data. So from this point of view, this means that this condition doesn't hold true. And 95% of all machine learners still use maximum likelihood estimation to train their deep neural networks. But this condition doesn't hold. So maximum likelihood estimation is just reasonable heuristic, but no theoretical guarantees. And this is what we see when we observe severe overfitting of deep learning models. This is exactly the direct consequence of the fact that maximum likelihood estimation is used where it actually should not be used. And during this summer school, we'll study how to apply Bayesian neural networks. Okay, so now let us switch to machine learning and see how we can build probabilistic machine learning models, and in particular Bayesian machine learning models. So let's use the following notation. Denote X as a set of observed variables, also known as features. Y would be the set of hidden variables or target variables, such as class labels or some other. And the task of machine learning is to come up with a prediction algorithm which is able to predict Y based on X. And the source of information is so-called training data set. There's the set of objects for which we know both X and Y. And we also have model, which is parameterized by theta. For example, weights of a linear model, or weights of a deep neural network, or thresholds in a decision tree. And we would like somehow to tune the model parameters, to tune theta according to our training data, so that to be able to predict the target variables Y for the new objects X, for which Y is not known. So in machine learning, there are generally two types of probabilistic models, so-called discriminative and generative models. So in discriminative model, we try to establish the probabilistic model, which is a joint distribution over Y and theta, conditioned on X. So X is always in the condition. So this model is more simple than generative model, where we have joint distribution over 3 groups of variables, and the obvious limitation is that using this model, we are only able to predict Y's based on X, but we're not able to generate new objects. We're not able to generate or predict X. So if our problem is, that does require us to generate new objects, we may use discriminative machine learning models. And according to the product rule, we can decompose this joint distribution as a likelihood function, P of Y given X theta, which shows how likely is to obtain the target variable Y if the observed variables for the given object were X, and if we used the model with the parameters theta. times P of theta. Formally speaking, I should substitute here P of theta conditioned on x, if we directly apply a product rule. But in most of our practical applications, the prior distribution on theta is usually assumed to be independent on x. So this is much easier, and this is pretty natural if we talk about machine learning models. So in many cases, for discriminative models, the space of y's is much simpler than the space of x's, and then this is very reasonable to use discriminative model if we're interested only in predicting y's. But for some modern machine learning problems, sometimes it happens that the space of y's, the space of the target variables, can be as complicated as the space of observed variables x's. For example, such problem is machine translation. When as an x we have a text on source language, and as a y we have text on target language. So the translation. Okay, and the second type of the machine learning probabilistic model is a generative model. So this is when we emulate the joint distribution over x, y, and theta. And again, we use this kind of decomposition. So this is our prior term, and this is our likelihood function, P of x, y, given theta. If we're not Bayesians, we simply omit the prior over theta here and the prior here, and then we use just classical probabilistic models. If we're Bayesians, we also establish the prior term here and here. So the main distinction between these two models is that using generative model, we can generate new objects, and the object is given by the pair of x and y. Okay, so now let's consider how we'll train our Bayesian models. So assume that we have training data, x train, t train. So this is the set of objects for which we know both x and y's. And assume that we have a discriminative model, and the model is Bayesian. So this is the joint distribution over y and theta conditioned on x. We do not model the distribution on x because we're not interested in generating new x's. We're only interested in predicting y's according to x. So the question to you guys, how do you think, what should we do at the training stage? If we have access to this probabilistic model, and if we have access to our training data. So what we traditionally do at the training stage? Well, traditionally, we're searching for the value of theta, if we're not Bayesians. But since we're Bayesians, right, we should apply Bayes' theorem. So theta is unknown parameter. It's somehow related to our training data, so we simply should apply Bayes' theorem and come up with a posterior distribution. So we start with a prior distribution, we substitute a likelihood function, likelihood of our training data, we apply Bayes' theorem, and we end up with a posterior distribution, P of theta given x train, t train, x train, y train. So this is the result of our training. Not a single estimate, not a single theta, not point estimate, but a distribution. So and distribution in some sense defines the ensemble in the space of models, in the space of our discriminative models. Okay, and if this is the result of our training, then what should we do? Yeah, at the test stage. Traditionally, what do? Well, if we're not Bayesians, if we use the frequentist models, the result of our training is maximum likelihood estimate, theta ml. And at the testing stage, we simply substitute this theta ml to our model, and we make a prediction. But now we're Bayesians. We do not have a point estimate. We have a posterior distribution over theta. So what should we do if we would like to predict y for a new object x? We condition it on the training data, and it can be written as follows using the product and the sum rule. And informally speaking, we perform weighted voting or Bayesian ensembling. So we use the whole ensemble of algorithms, the whole distribution which we obtained during training stage, and we perform voting with respect to this distribution. So we simply average the predictions given by different thetas, and we weigh these thetas according to our posterior distribution. And we take the integral. So that this average prediction is the result of of applying our Bayesian model to new data. And this is very important. So instead of using just single algorithms, we use the whole ensemble of algorithms. And in practice, surprisingly, it appears that such weighted voting really improves the accuracy. So everyone who used, for example, binary dropout in your deep neural networks and tried to average the results at the testing stage can confirm that such averaging generally increases the accuracy in comparison with the application of just single algorithm or just single dropout run. And this happens because dropout can be regarded as a particular very rough approximation of some Bayesian model, which we'll study during this summer school. So this was confirmed by numerous experiments held both in our group and in many other groups, that this averaging really helps. It allows us to get better uncertainty estimates, but it also allows us to get better accuracy, for example, if we are talking about the classification problems. So to summarize, at the training stage, we apply Bayes' theorem. At test stage, we perform ensembling, and we average the predictions by different algorithms with the weights proportional to the posterior distributions. And what's the problem here? The most computationally expensive parts are, of course, those integrations. And as was noted, it's not obvious whether these integrals can be taken in closed form. And we all know from the calculus courses that integrals can be split into two groups, the tractable and the intractable. So for tractable integrals, everything is okay, but if the integral is intractable, then there's no hope that we can numerically get any reliable estimates for the integrals. Why? Because the space of integration is usually huge. For example, if we speak about Bayesian deep neural networks, the space of theta can be up to tens of millions. In such huge dimensional spaces, there's no hope in getting any reliable numerical estimates for those integrals. So of course, we'll study some approximate Bayesian inference tools, but first let us consider the special case when those integrals can be computed in a closed form. And this is a case known as conjugate distributions. So by definition, parametric families for the prior and for the likelihood are called conjugate if the following holds true. So if our prior belongs to some parametric family A parameterized by parameters alpha, and our likelihood function belongs to some parametric family B, which is parameterized by Y, because Y is in condition here, and if we can prove that our posterior distribution will also belong to the same parametric family as our prior, but of course with different parameters, alpha prime. So if this property holds true, we say that these two distributions are conjugate. And this means that we can perform full Bayesian inference or in a closed form. So the intuition is pretty simple. If we know that the outcome is the posterior distribution belongs to some parametric family, this means that it's correctly normalized, and this means that we know its normalization constant, and as a consequence, this means that this integral can be computed in a closed form. And then if we have the pair of conjugate distributions, and if we would like to apply Bayes' theorem, all we have to do is to recompute this alpha prime parameter, because it fully defines the closed form for posterior distribution. Okay, so now let's consider some examples. So again, return to our example with a tossing coin, and establish the following Bayesian model. So this is joint distribution over x and theta. X's are the outcomes of particular coin tosses, and theta is the probability of a head. So using the product rule, we can decompose it as follows. So this is a likelihood function, which shows how likely it is to observe the given outcomes, and the prior distribution over theta. As for the likelihood function, we know how to write it down. So this is simply a Bernoulli distribution over x. Or equivalently, this is theta to the power of x times 1 minus theta to the power 1 minus x. So if x equals to 0, this means tail. And then we have 1 minus theta. This is the probability of tail, exactly. And if x equals to 1, then this distribution equals to theta, and this is exactly the probability of a head. So this is our likelihood function. Okay, so now the question is, what should be our prior if we want to operate in terms of conditional distributions? If we want to be sure that we'll be able to perform full Bayesian inference. So to do that, we need to establish prior distribution which belongs to the conjugate family to this Bernoulli distribution. So the question is, what distribution family is conjugate to Bernoulli? So let us see. So I suggest to use so-called beta distribution. And beta distribution is a parametric family of distributions which is parameterized by two parameters a and b. And by definition, its density is given by this equation, where theta lies between 0 and 1. So here on the plot you see different probability density functions for different parameters of a and b. And let us prove that this distribution is really conjugate to our Bernoulli likelihood function. And by the way, here what's important is that this distribution, its support is from 0 to 1. So this is correct if we tell about the setting of prior distribution over the probability, which cannot be less than 1 and cannot be more than less than 0 and cannot be more than 1. And what is also nice is that inside this distribution we can always select such values of a and b that the distribution will be unimodal and its mode will be around 1/2. So this reflects our nature preferences on the probability of a head. Because the most of coins in our life are fair. So we know that most likely the probability of a tail would be around 1/2. And we would like to encode this information in terms of our prior distribution, but to be able to do that, we need to set such family of distributions where the unimodal distribution with a mode at 1/2 is contained. And beta distribution is exactly such kind of distribution, and we can always set such parameters a and b that this distribution would be bell-shaped with a mode at 1/2. Good. Now let us prove that these two distributions do conjugate. So our prior distribution has the following form as a function of theta. So this is some constant times theta to some power times 1 minus theta to some power, right? So this is the functional class. This is how our distribution looks like as a function of theta. So what can we say about posterior distribution? So again, up to some normalization constant, this is simply product of our likelihood function times our prior. And our likelihood function is theta to the power of x times 1 minus theta to the power of 1 minus x. And here we substitute our prior distribution. This is it, and we easily see that this function, as a function of theta, has the same form as our prior distribution. So this is some constant, c prime prime, times theta to some power, so we simply rearrange the terms here, times 1 minus theta to some power. So the form here, the functional form here is exactly the same as the functional form for our prior distribution. Conclusion, these two distributions are conjugate. And this means that we can obtain the posterior distribution in a closed form. Moreover, we may conclude that the posterior distribution would still be beta distribution, but with different parameters, because it has the same functional form as our prior distribution, and only the values of parameters has changed. Okay, so now let us have n outcomes of tossing a coin, x large, and let us derive the true posterior distribution. Up to normalization constant, this is a product of likelihood times prior, and the likelihood of our observed data is the product of likelihoods of individual outcomes, xi's. So, and here we substitute the prior, we substitute the likelihood, we rearrange the terms, and we end up with this expression, so some normalization constant. We do not care about it because we know that the resulting distribution would be beta distribution, and for beta distribution we know how to compute the normalization constants. And here's the parameters of the beta distribution. So this is beta distribution with the parameters a prime, b prime, where a prime equal to these expressions. So this is a plus the summation of xi's, and the b prime is b plus n minus the summation of xi's. So these are the new parameters of our beta distribution. And the beta distribution with these parameters is now our true posterior distribution. So we managed to perform full and exact Bayesian inference in a closed form. And here we use the fact that the prior and the likelihood function were conjugate distributions. And actually, there are not so many examples of conjugate distributions, and some of them are shown here. More of them you may see, say, in Wikipedia, if you type conjugate distributions. Those couples of distributions are well known. Unfortunately, the problem is that this is very rarely the case when in our probabilistic models we have a chance of working with the conjugate distributions. Generally, the conjugate distributions are only applicable when we speak about very simple probabilistic models, such as, for example, linear regression. But if we switch to more complicated models, such as deep neural networks, it already appears that no reasonable prior conjugates with a likelihood function which is given by deep neural network. So in most interesting applications, we have to do with the non-conjugate distributions. Maybe we may say unfortunately, maybe we may say fortunately, because if we always worked with the conjugate distributions, then probably I wouldn't be professor in high school economics, and I would be some unemployed guy, because this is actually one major part of my work. Okay, so now the question, what can we do if we do not have conjugacy property? So if our prior and the likelihood function doesn't conjugate. And one of the most simple ways out is to use MAP estimation, or maximum posterior estimation. So this is simply searching for the mode of posterior distribution. And we know that the up to normalization constant posterior distribution equals the product of likelihood times prior, according to Bayes' theorem. So in denominator, there's some normalization constant which doesn't depend on theta, so we may simply skip it. And then it appears that this argmax equals to the argmax of the product of our likelihood times prior. And this is sometimes called poor man's Bayes, or Bayesian inference for poor. This means that this can be done very efficiently. No integrations are involved, and still we have some kind of regularization of a maximum likelihood estimation. And every one of you who used, for example, L2 regularization of weight decay during training your deep neural networks actually did exactly that. Poor man's Bayes. Because you correct maximum likelihood estimate, instead of searching for the maximum of likelihood function, we search for the maximum of product likelihood times prior. And L2 regularizer corresponds to Gaussian prior with a zero mean. Okay, why it's also quite suitable for practical purposes? Because not only we may easily find this theta MP, but at the testing stage, again, since we are Bayesian, we should perform this kind of integration. But now our posterior distribution collapses to single point. So we try to approximate the true posterior distribution with a delta function at one point. And this is the point of maximum. And then this integral collapses, and we simply substitute theta MP in our likelihood function and predict value of y given the features of a new object x. So this is computationally efficient. No need of integrating, no need of computer normalization constants, but of course, we lose lots of information. When we switch to point estimates, we lose many advantages of Bayesian framework. There's no ensembling anymore here. There are no good uncertainty estimates because there's no weighted voting here. But still, this is one of the possible ways, probably the easiest one. But hopefully, fortunately, not the only one. And we'll study more elaborate techniques during next lectures. So it geometrically corresponds to something like that. So we had a true posterior distribution, and we approximated it with a delta function. So the question is where to put the delta function, which is the most representative. And the mathematical answer is that we should put it at the point of mode, and it can be justified using some information theoretic considerations. Okay, so this is it, and probably this is the end of my first talk. Right. So if there are any questions, I will be happy to answer. Well, yes, they're connected somehow, but not in the way you are speaking about. The similarity between common filters and what I was talking in this lecture is because common filter itself is a Bayesian model. Only do that. So this is not a mixture of deep neural networks with a common filter. It's a mixture of deep neural networks with a Bayesian framework. And common filter is another example of a Bayesian model. But it's different. So it has no relation to deep neural networks, at least in its original form. And here we do not mix deep neural networks with common filter. But the mathematical tools which we'll use will be pretty similar, but not because this is the particular case of common filter, but because common filter is a particular case of Bayesian model. Yeah.
Hi, I'm sorry. I drifted away a bit when we were talking about quantum mechanics and randomness. And maybe you could repeat this part or elaborate a little bit, because that sounded like something I haven't heard before.
Okay, but actually it's not related to our summer school. It's not related to machine learning. This is some general knowledge. Well, in quantum mechanics, we have so-called indefiniteness relation by Werner Heisenberg, which states that we cannot define with arbitrary high accuracy the parameters such as speed and such as coordinate. And the direct consequences of these indefiniteness relations are the fact that there are some values in quantum systems which cannot be defined. And this is sometimes called a superpositional state of quantum system. And when I told about randomness as something, as a result of some process which cannot be predicted by somehow, I meant exactly that. And the practical example is radioactive decay, for example. We have unstable particle. At some moment, it collapses into, it splits into two or more parts. And we cannot predict the exact moment when this unstable particle will be split. We know that it will be split. We can compute some statistics of radioactive decay, but we cannot predict the exact time of splitting of a particular particle. So this is the example of a random variable, which is random from Frequentist point of view. And this is this is the direct consequence of the fact that radioactive decay should be considered as a quantum system and should obey the laws of quantum mechanics. And by the way, one more remark, if we started discussing quantum mechanics, I think that such analogies is fair, although I may be wrong, but at least I like this analogy. In some sense, Bayesian framework can be considered as a quantum mechanic of probability theory, just as a Frequentist approach is a classical mechanics of probability theory, and Bayesian framework is a quantum mechanics. Why so? Because instead of working with the point estimates, we work with the distributions. So when we perform Bayesian inference, and when we end up with a posterior distribution over the weights of, say, our neural network, in some sense, when we say that our neural network is in superpositional state. We don't have just one neural network, but our neural networks simultaneously may have different values of the weights. And we should keep them all into account at the prediction stage. And we do this by performing Bayesian averaging or ensembling. And this is, again, exactly what we do when we work with the quantum systems in superpositional states. We also compute some kind of expectation with respect to all possible states of a quantum system. So I like this analogy. I realize that I may be wrong, and the origins of these uncertainties of this superpositional may be completely different, but still, this is pretty nice. Okay, thank you.
Can I speak into my mic?
Yes, sure. Could you repeat the philosophical difference between the frequentist and Bayesian thing that you spoke about? I have heard about it in different contexts, but then I think the one that you mentioned was quite interesting. But I zoned out when you were explaining about it.
So you want
So
me
it was so frequentist was like something about it cannot be predicted by any means, and then Bayesian was
yeah.
completely deterministic process. But that's the only note that I got from the whole thing that you spoke about. Could you just repeat the thing that you
Just repeat?
Yeah.
Okay. So once again, this is conceptual, philosophical level. This is not mathematical level yet. But from philosophical point of view, the two approaches differ by understanding what is randomness. So from classical point of view, randomness, random variable, is the result of some process which cannot be predicted by any means. So it's unpredictable. We can only collect some statistics of the outcomes of a random process. And from Bayesian point of view, random variable is the result of some deterministic process, but some factors which influence its outcome are unknown for the observer. And only due to the lack of knowledge, the outcome looks like random for us. And different observers may have different knowledge, may have different lack of knowledge, and this is why for different observers, the distributions can be different. And these differences arise because we condition on different information. So for example, let's consider the following example. Assume that I'm waiting for the bus at the bus stop. And I have timetable. And can you still hear me? Yeah, good. And timetable states that the bus should come at 10:30. I don't know whether there are any Germans here. In Germany, probably you may update if the bus arrives, say, 10:29, then something is wrong with your watch. You should update your watch. But in Russia, if the timetable states that the bus arrives at 10:30, it means that, well, it may arrive 20 to 40 minutes past 10. Somewhere like this. And this is my... so actually, the exact time of arrival of a bus this is a deterministic process. So there is no randomness in the classical point of view. The bus arrives at a specific time, and we can even knew all its current location, even knew the phases of traffic lights, even knew whether there are traffic jams or not. We could predict the exact time of bus arrival. And only because I don't know all that. For me, the exact time of bus arrival is a random variable, and I may say that, well, this is a random variable, and I can probably construct probability density function that will be bell-shaped, and we'll have a mode at 10:30, and we'll have some variance. And now consider that my friend comes in, and he uses, well, the application, Yandex Transport, so-called, which shows the exact location of each bus. So he turns the application and says, aha, the bus is three streets from here. So it should arrive approximately at 27 minutes past 10, plus minus 1 minute. The exact time of bus arrival is still a random variable, for him as well. But he has more information than I had. So, he has different uncertainty. So he still has a distribution, but this distribution is also bell-shaped, and it has mode, but already at 27 past 10. And its standard deviation is much smaller than my standard deviation. But this is still a random variable. So we have different observers with different lack of knowledge. So this is what I wanted to say.
Yes.
Okay.
Hi, my name is Mahmoud. I'm from the University of Virginia. I'd like to ask, what is the difference between ensembling under Bayesian framework and ensembling using other methods like, for example, random forests?
Well, the difference is that in classical ensembling, you simply train several algorithms independently, and then you try to average their predictions. Here, you perform training just once, and you come up with a distribution, with a posterior distribution, from which you may sample the particular samples of theta, of your weights, and thus obtaining the members of ensemble. And ideally, in theory, you should ensemble with respect to continuum number of different prediction models, because you have a distribution in a continuous space. So this is the difference.
Thank you.
Well, as for uncertainty as the source of randomness, we said that if the bus is coming right now, but it hasn't yet come, then the time of its arrival is a random variable. Well, people who work in analytics, they used to provide confidence intervals, credible intervals, and whatever for things that are already done, that have already happened, I don't know, the number of sales, the number of people who came to this conference. Most certainly you can compute credible interval for the number of people who came here. And what is the source of randomness here? Why the thing that already happened is random, or it is not, or is it not?
Well, this is exactly what I was going to ask you. I do not understand why should we use confidence intervals to estimate the number of people who are already here. We can compute them in a closed form.
Well,
there's no need of estimating confidence intervals.
Yeah. For the number of people, there is no need, but for, I don't know, the percent of applications, when you are an analyst, you have to compute confidence intervals.
Well, I would assume that the only reason why you need to compute the confidence intervals is because you're not 100% sure about your measurements. For example, you have the amount of sales. It is reported to you by, well, some supermarket network, and you may suspect that, well, they may be mistaken, they may measure the exact number in the wrong way, or they may deliberately make some distortions in this number. Yeah. And this is why you are establishing confidence intervals, because you're not 100% sure.
Yeah, so the source of randomness is lack of information, still the lack of information. Okay,
Right.
Thank you so much.
Okay, let's have the last question. Sorry, please use mic.
Hello, thanks again for your lecture. When you're talking about interactability in the evidence part, like in the creation, so beside all the approximation that we are doing here, or all kind of divergence or KL divergence or other kind of method that we are using to do the approximation, so is there a kind of method, like kind of mathematics method or computational ways to do that to solve this part, like recently or something like new?
To solve what part? You mean
to solve the interactability part, like the integration that we have inside of the evidence?
Well, as far as I know, no reliable tools still exist for the high-dimensional spaces. So let us... Okay, here we go. For example, this denominator. So there are some approaches where we try to perform Monte Carlo estimation. So we sample from this distribution, we substitute here, and we remove this integral to Monte Carlo estimate. But unfortunately, you obtain unbiased estimate for the integral. But unfortunately, its variance is huge. So when we consider the integrals in the space of, say, 10 million of dimension, you need an astronomical number of samples in your Monte Carlo estimator to be more or less accurate. So no reliable techniques exist, at least to the best of my knowledge, for estimating such kinds of integrals. What is good is that we can estimate this integral in a pretty reliable way using Monte Carlo estimation. Because here, well, the variance of this function is not too large. And so you may use, say, 10, 20, 100 of samples from this distribution, and that would be already enough to get very good and reliable estimate for this value, but not for the evidence value in the denominator in Bayes theorem.
Okay, thank you.
Okay, we still have time.
Okay, so from your lecture, I got a gist that it's crucial to actually be able to encode some information in that prior distribution we're using. But and this works fine for small examples like the coin toss, right? But how do you start to reason about the prior when you're trying to fit over a data set that it's composed of images, for example? How do you start to think about the prior distribution there? How do you encode that information? Because it doesn't seem trivial to find a distribution that kind of says something about that data set. So,
well, actually, we should establish prior distribution without seeing the training data set. Otherwise, there is a risk of overfitting. Although such approach also exists, known as empirical Bayes, and it will be considered in one of the following lectures on Saturday or Friday, on Sunday probably, yeah, on Sunday. But again, I would say that there's some general tool of how to establish prior distributions. So prior distribution is something you choose yourself, using your preferences or your uncertainty about the possible values of unknown parameters. Sometimes it's not easy, that's right. But in many cases, it's easy because by setting prior distribution, you provide some hints to the computer of what it should obtain as the outcome. For example, if you're familiar with the topic models, with the latent Dirichlet allocation, are you? A little bit, yeah. So there's a very natural way of how to establish the prior distribution over the weights of topics in the document or over the weights of words in the topic. Because it's highly desirable to have very sparse representations for topic profile in the document, and it's highly desirable to have quite sparse representations for each topic in your vocabulary. So you establish prior distribution, which is sparsely promoting. But this is, again, some particular case. As for the general case, well, again, I would give you just one example. If you train even one deep neural network with, say, 10 million of parameters, and you build a histogram of its weights, or trained by maximum likelihood estimation, and you build a histogram of its weights, you obtain a bell-shaped curve which looks pretty much like zero-mean Gaussian. And so this, again, provides you some hints of how you may set prior distribution. That if you set it by zero-mean Gaussian, then probably you'll be more or less okay, and you'll be in correspondence with your maximum likelihood estimates. So this is a quite reasonable way of establishing prior distribution by using zero-mean Gaussian when we speak about deep neural networks. But in general case, the question is open. Yep. So there's no general tool of how to set prior distribution without, well, some human involvement. Probably the only possible way is to use empirical Bayes that we'll consider on Sunday.
Thanks very much. So the question is about the testing of Bayesian models. So we compute the posterior predictive distribution, and we collapse it somehow to a single prediction if the problem asks for that. But the question is whether this Bayesian prediction just happens to be better than ordinary frequentist prediction, or is there some deep underlying principle which says that, well, this posterior predictive approach is somehow better aligned with what we really need? Because what we really need in the problem formulation doesn't call for a Bayesian approach. It doesn't call for any distributions. It just says, well, give me the translation of this sentence. And why does the Bayesian approach just happen to deliver better results, or is there some underlying principle?
Okay, I got it. Well, I would say that this equation is, in some sense, justification of why a Bayesian approach should work better. So if we have a realistic model, what we actually care about during the testing stage, we care about this value. Why? What this value states? It states what is the probability of y for the given object x if the only information we had was our training sample, because this was the only information we had, the only source of information using which we are trying to come up with some prediction algorithm. So we should condition our prediction not on theta, but on our training data. And this is exactly this quantity. And if we try to write it down, we'll immediately get this equation. So the only way how we can relate our training data to our prediction is theta, because this is our prediction model. And for theta, we should first condition theta on our training data. This is posterior distribution. And then we should average the results of prediction of single algorithms with these ways. And by doing this, we'll obtain exactly the expression in the right-hand part. And this is what we really care about. So we not care about predicting P of y given x and given the specific particular value of theta. This is not natural. So the natural way is to condition our prediction on the observed features of a given object and on the training data. So I would say that this is some kind of justification of why we should perform Bayesian averaging.
Maybe we could also say that in this Bayesian way, we consider the uncertainty, like naturally the uncertainty about the parameters and also uncertainty about the input data is considered, while in the frequentist way, it is not.
Well, it is also possible to consider the uncertainty about the input data. If by input data you mean x?
Yes,
yeah.
Like the training instances
are not measured in an exact way.
Yes,
but
exactly.
Yeah.
Considering it a distribution, like having a distribution over all weights and the output of the network, I assume like the output of the networks would be a representative of the input data.
Well, we can definitely take into account the uncertainty with respect to inputs. And for example, just for simplicity, assume that we have uncertainty here. So we're given object x, but we're not 100% sure about this particular value. So actually, there's well just some distribution in the space of x's. So we may easily take it into account in this equation. And then here, we should also average with respect to the distribution over x's. And we'll get correct prediction with the correct uncertainty estimates. It's more complicated to consider the case when the training sample, the training data itself is measured in an inaccurate way. To tell the truth, I'm not familiar with such kind of models, but I assume that they're also possible. And probably, you can derive the way of how to compute this posterior distribution in the case when x train and y train are not known in the exact way. And there are some uncertainties in their values as well. I think we may continue questions in the lobby because now it's time for coffee break. So we have 20 minutes break, and then we'll continue with the next lecture about variational inference as one of the most popular approximate Bayesian techniques.